this button here, and I think it's that we became YouTubers now. Okay, let me check if it's live. I think so. So welcome everyone, good morning. This is our international seminar series in ecology at the graduate program of ecology at URGS, or the Federal University of Rio Grande do Sul. And I have the pleasure to introduce you today to Professor Rampal Etienne from the University of Groningen in the Netherlands. Rampal works with theoretical ecology, evolutionary biology. He has made very important contributions, especially to the fields of community ecology, biogeography, and macroevolution. For instance, he did theoretical extensions to the neutral theory of biodiversity, and recently he did a new method for state-dependent speciation and extinction. And besides that, of course, he works with Island Biogeography Theory, which is the subject of his talk today. I also want to thank you, and I'm deeply honored to have you here, Rampal. And forget to talk, he is also contributing in our graduate program here. He is currently advising two PhD students. So on behalf of the program, I want to thank you very much for being here today. And you can speak anytime you want. Questions from our audience can be posted in the chat of YouTube during or after the talk. Okay, you can start at any time, Rampal.
Okay. Well, bom dia to everyone. And obrigado to you, Renan, for inviting me. Well, those are the only words of Portuguese that I can speak, I guess. Well, maybe a few more, but I will do the rest in English. I have just one question about whether if people actually put something in the chat, can I see that immediately, or?
I don't know. Do you see the chat in the right here?
Yeah, I see on the right. I see private chat. Chat with the host and other guests.
Yeah, that's a chat. I don't think you are going to be able to see that while you're presenting your slides.
Okay.
But after, yes, for sure.
All right.
After, yes.
Okay. Let me just start up my presentation then. So I have it here. So today we'll be talking about next generation island biogeography. And basically, I actually hate the word next generation because it's always something about the future, but it's happening now, right? It's the same with next generation sequencing methods. It's just, we don't know what the next generation is. If we knew, then it wasn't the next generation anymore. But I'm still trying to say something about what I think is the next, in fact, current step in island biogeography. And so islands are intriguing. So maybe for many of you, it's not an issue of actually studying islands. It's very natural to do this. But for those that might be skeptical, here are some answers as why islands are so interesting to study from a scientific point of view, rather than just because they're nice and beautiful in many cases. And one of them is that they're isolated. So they make up a sort of a simpler system than just any ecosystem. Also, in an archipelago, there's also some kind of replication of islands, which is also very nice from a scientific point of view. Many of these islands are, of course, unique, with lots of endemic and unique species. And because of that reason, they're also of high conservation priority. There's unfortunately a lot of species going extinct and having gone extinct already on islands. So we really have to focus on islands for that reason as well. Okay, and we're focusing mostly on marine islands. And so I've drawn here a map of the world, but only in terms of islands. And what you see is you might think, hey, what's wrong with my eyes? But that's because I've only drawn here the islands rather than the actual mainlands. And so you see that actually the islands are everywhere in the world, these marine islands. And they host also the most unique species. However, marine islands are not the only islands that exist, at least from a theoretical point of view. There are also things called sky islands, which are mountaintops, which are also isolated and have also this feature of replication, and also unique. And there is also something called marine lakes, which are sort of inverted islands, because they are not land masses surrounded by water, but they're water surrounded by land mass. And these are marine lakes, for example, in Southeast Asia, but they function quite in quite the same way as oceanic marine islands, in that they are isolated from the ocean. And there is some colonization of these lakes possible underneath the ground, but it's limited, like you have for regular islands. So for all these different islands, you can develop a theory. And of course, I'm not the first one to do this. The most important pioneers in island biogeography have been MacArthur and Wilson in the 1960s. And perhaps maybe from your ecology classes, you might remember this plot here, where the rates of colonization and extinction are plotted versus the number of species on the island. So they argued that as the number of species on the island increases, the rate of extinction will increase, and the rate of colonization will decrease. And where they meet, where they intersect these lines, you will find the equilibrium number of species that you would expect on an island. And so they also argued that it depends, of course, on how far the island is away from the mainland, whether colonization can take place easily or might be harder, and that depends on whether they're near or far, as you can see here. So then also the equilibrium number of species, so the intersection point, will shift depending on whether it's far or near the mainland. Well, similarly, if islands are large or small, also will influence the extinction rate. Where if they're large, extinction rates will be lower, and so the equilibrium number of species will shift to the right for large islands. Now, this theory of island biogeography has been very important, but there are some things missing in this theory. It's mostly an ecological theory. So in MacArthur and Wilson's 1967 book, which is really a classic work that really sets the stage for island biogeography, they do mention evolution, and they do talk about evolution, but it's only scarcely mentioned, and it's only and they actually don't really include it in their model. They don't talk about speciation. But that's quite odd, maybe, because many oceanic islands have high degrees of endemism. So speciation must be essential. Speciation must have happened on these islands if there are endemic species there. Unless you explain this endemism by extinction on the mainland, but that would be quite a rare case, I would say. But this might also be just because it's really mostly an ecological theory rather than an eco-evolutionary theory. So we want to do something about that, and in fact look at these more macroevolutionary timescales, and then ask some new questions. And these are, well, maybe not new questions anymore, because we've been asking these questions over the last couple of years. And so these questions are, first, are island biotas actually in equilibrium at evolutionary timescales? So MacArthur and Wilson assumed this in their model, that the systems are in equilibrium between colonization and extinction at ecological timescales, but are they also in equilibrium at evolutionary timescales when you take into account speciation? And particularly, you can ask, are there actually ecological limits to biota assembly? Can we always just put more species in there, or is there a limit set by ecology? And you can also then rephrase that by saying that our diversification and immigration, are they dependent on diversity on the island or not? Now, second question is also very important on islands, is what's the anthropogenic effect on island biodiversity from a macroevolutionary perspective? So we know that lots of species went extinct on islands, particularly because humans arrived there and just drove those species to extinction. But what can we, from a macroevolutionary perspective, can we say something about the magnitude of that effect? That's the second question. So third question is, when we look at radiations on islands, and maybe one of the most familiar to you will be that of the Darwin's finches on the Galapagos Islands. Those are radiations where multiple speciation events occurred. And we see that on quite a number of islands, but are they actually exceptional, or are they consistent with the rates, the background rates of species gain and loss? So that's the third question that we would like to ask in island biogeography. Now, to go to that last question, whether something is exceptional or not exceptional, maybe just some examples of these classic insular adaptive radiations, like silver swords on Hawaii, or anodous lizards in the Caribbean. The Darwin's finches are already mentioned, but also the vangas on Madagascar are classical cases of, on an island, you have many speciation events, one after another in a single clade. So is that exceptional, or is it sort of still part of the rule? Now, then there are two further questions in island biogeography. So how do the community assembly processes on the island depend on island characteristics, and particularly on the area, as I was mentioning already before in MacArthur and Wilson's theory, where they said the extinction rates are depending on those characteristics. And the last question is, how do processes of community assembly on islands depend on the species that are already present on the island? And I will get back to what I actually mean by this question later on. And we're also living in an age, of course, of where there's lots of molecular data available, and phylogenetic trees are being constructed for all the species that we find on islands and also outside islands, of course. And can those phylogenetic data, so this new data that we've been collecting over the last 20 years, say, can they actually help us answer these questions better than we could before with just counts of species and knowing whether they're endemic or not? Now, so what we'll be talking about is our vision on what's next generation island biogeography is to actually unify island biogeography, as MacArthur and Wilson saw this, with clade diversification. So where there is really speciation incorporated in the theory. So what we have on the one hand is a species input, which is immigration, which was also present in MacArthur and Wilson's theory, and in situ speciation, so speciation happening on the island. And we have species loss by extinction, as in MacArthur and Wilson's theory. Throughout the talk, I will be denoting these various processes by the Greek letters for their rates, just to keep it short. But I will probably mention the words just to explain if these symbols again. So gamma stands for immigration or colonization. And mu stands for the rate of extinction. And then we have two lambdas, lambda C and lambda A, which both stand for a form of speciation, where lambda A is anagenesis and lambda C is cladogenesis. And so by lambda A, by anagenesis, I mean that an island species can just become different from a mainland species, and you can call that speciation just because it's isolated and there is very low or even absence of gene flow will create, after enough time, will create a new species on the island. Or in fact, you could even maybe better say is that the island species and the mainland species diverge enough from each other to call them different species. And there's also cladogenesis, which is in situ speciation, where on the island, an island actually splits into two species. Often this could also occur on an archipelago, where it's not really sympatric speciation, but it's allopatric speciation, but on the archipelago, where different islands might host different species that have speciated from a single ancestor. So these are the processes that we'll be considering. And then the question is, answering these key questions that I mentioned before, for example, on equilibrium and radiations, etc., requires knowledge of these rates. So if we can estimate these rates, then we can actually use these rates to simulate the processes again and see whether, how we can answer these questions. So this is what we set out to do, to try to find ways of estimating these rates from phylogenetic data. Now, before I do so, I would like to introduce first a model. So there is only a few slides of maths, with equations in this talk. So don't be afraid. Don't go away yet. But of course, I have to introduce a little bit for those that are a little bit more mathematically oriented. And so for a simple understanding of what's going on these islands, you could make a model of the number of how the number of endemic species on the island changes through time, and the number of non-endemic species changes through time. Now, so we denote those by E and I, and then we also have an M for the number of species on the mainland. Now, if we assume that all these rates are constant, we can write down equations for the rate of change in the number of endemic species and the rate of change in the number of non-endemic species. And so what you will see is that they will depend on cladogenesis and anagenesis, of course, and extinction in the endemic species, whereas the non-endemic species, of course, depend on colonization from the mainland, and they will be lost when the non-endemic species turn endemic. And of course, they also will be lost if they go extinct. So that's what's written in these equations. But what's interesting is to look at the solution. And again, maybe forget about this formula. What's most important to take away from this is that we only will achieve an equilibrium if the extinction rate is larger than the rate of cladogenesis. If not, then you actually won't have this equilibrium. You won't have an equilibrium. They will just, if cladogenesis is larger than extinction, it will just continue to collect more species on the island. So the non-endemics also reach equilibrium faster. This is what you can tell from this from these formulas, and you can tell this if you want to know more about this by looking at the exponent of the exponential function, is where you see in the non-endemics that there is a sum of all the rates, and the larger that sum, the larger the faster the equilibrium will be reached. So non-endemics reach equilibrium fastest, and it will only be later followed by the endemics, which reach equilibrium at a rate mu minus lambda c. All right. But this is a deterministic model just to get a little bit of an idea of the dynamics that are going on. But really, if you want to look at real data and try to estimate parameters from those data, then it's much more useful to look at a stochastic framework, to look at a stochastic model. And so for this, we developed what's called our DAISIE model. And DAISIEs are, in fact, one of the key radiations that are observed on islands, so in the sunflower family. And but it stands actually, it's an acronym, and it stands for Dynamic Assembly of Island Biotas through Speciation, Immigration, and Extinction. So it includes all these processes that I just talked about. And so this framework is a fully stochastic framework. It allows simulation of islands according to these processes, but also provides a likelihood of phylogenetic data from which we can estimate these parameters. And furthermore, it also allows diversity-dependent diversification and immigration. And this is why this letter K or K prime is in this figure, because it stands for the number of species that can be maximally there, and because for larger numbers of species, the colonization rate would be zero, and also the diversification rate will be zero. So you never reach those larger numbers. So it's sort of really a maximum to the number of species that can exist on the island. Now, so if we can incorporate that to answer some of our questions about diversity dependence, and I will get to that later. So the parameters that we can estimate using these likelihood methods, they can be used for stochastic simulations again. So let's see how we do that. And these are, sorry, I forgot to mention one thing, is that about the diversity dependence, is that there is two types, and I'll also get back to that later. There's clade-specific diversity dependence, which means that it only applies to diversity within the clade established by the mainland ancestor. So you have a mainland ancestor that's colonizing an island, and then it might diversify on the island, and all its descendant species, they might be limited by each other's presence, in the sense of that they will diversify more slowly, or if the mainland ancestor would re-immigrate, it would have a harder time to re-immigrate because there's already species there that are similar to it, because those are its descendants. So that's the clade-specific diversity dependence, where it only applies to that one mainland ancestor. The other extreme is an island-wide diversity dependence, where in fact all the species on the island affect each other, regardless of who the mainland ancestor was. So any species that will colonize the island will experience a lower rate of colonization and a lower rate of diversification if there is already other species around on the island, regardless of what ancestor they actually descended from. So those are the two extremes, island-wide, so for all the species on the islands, and clade-specific for only for those that descend from a single ancestor. Okay, so before I continue on this, I would like to actually say something about how we, in fact, score sort of when we look at data, how we what that means for our calculation. So here we have a typical data set of 5 colonizations, where the species, where the clade A colonized, so the ancestor colonized first. That's the blue one at the top, and then split into 2 species later on. And then we have a second one colonized a little bit later, and in fact there was, of that same ancestor, B, was a recolonization after some time. And then there's also a colonization by species C and a colonization by species D. And so I've also included some dashed lines here, is because in some cases we might actually not know when they immigrated, if they are non-endemic species, because we would then have to have data on the island species to be able to know when they diverge from their mainland sister species. Now, I won't go into the details of the second graph, but I would like to tell you that in calculating all these things and calculating the likelihood according to island-wide diversity dependence involves massive computations like this, and so a lot of thinking to do this and a lot of coding to get this right. And I will skip over the details of this, but just to give you an impression is that a lot of time is spent on in fact finding these equations and getting them right into in our computers and doing the right stuff with them. And then once we've done that, we want to use those formulas to actually apply this to our DAISIE input. But what is our DAISIE input actually? So what we use for this is we start, of course, with a phylogeny. So in this case, we have a phylogeny of a number of species, but not all these species are, of course, on the island. So this is the question is, so how do we translate this to DAISIE? So we have some islands on the species on the island that are endemic, and some are non-endemic. And so we also know that at some point in the past, the island came into existence. So, of course, before that time, they couldn't have colonized the island because the island wasn't there, right? So we have to take this into account and then see what does the typical data look like when we start with this phylogeny. Now, so let's look at the top one. So we see the T12, that species there. In fact, what we see is that it's we know it's a non-endemic. We can tell because it's also present on the mainland, right? And then the question is, when did it actually immigrate? Well, we know that the species T18 is present on the mainland, but not on the island. And so what we then say is that, well, the divergence time between the T18 and T12 must have marked the divergence, well, must have marked the colonization of species T12. So, but it could have also been after that, because it's a non-endemic species. So anywhere between the 2 green dots on the right, the species might have colonized. So that's one step. Then we go to the second, this blue singleton endemic species. And so here, I see that there's a bit, the blue dot is in fact missing, but what we see here is for T10 is that we know that it diverged from T18 at a certain time, and that divergence time marked its colonization. And it must have happened then, because the argument is that once it colonizes the island, it will be separated from T18, and this is what marks the actual colonization event. So this is what we do for T10. Well, we can then also look at the clade that we have here for an endemic clade formed by T16, T19, and T5. So this is a clade that is formed on the island. And so what we say is that our crown age is, we know that for that island, but the immigration for that of that clade, of the ancestor that colonized the island, we don't know that. And when we look at the most closely related mainland sister species, that actually the divergence time from that with T6, for example, that divergence time happened before the island came into existence. So we know that there must be something must have happened in between that. Maybe the mainland sister species went extinct, but the only thing we can say is that between the island age and the crown age of the clade, the species must have colonized. Now we can go on like this with the other species on the island as well to really mark. So what do we know about colonization and branching on the island for these different species? So this is how we, in a nutshell, really go from the phylogenetic information that we have in general to the DAISIE input. And what we also see is that we don't need really a full phylogeny of all the species of this particular clade. Of course, we need to know all the information for the island species and for their most related mainland sister species. But that allows us to do actually analyses on even much larger clades where we don't often have the phylogenetic information on all the species on the mainland. But as long as we have this information for most of our, for all of our, well, at least all of our, most of our island species and their sisters on the mainland, we can get quite far. Okay, so we use this type of data. So here's again an example for the birds on the Galapagos. We feed this to DAISIE, and we then estimate our rates of colonization, extinction, cladogenesis, and anagenesis. Okay, so you may wonder, though, how much do these phylogenies really add to the story, right? Do we really need all that phylogenetic information? Well, in the past, people were using mostly diversity, just the numbers of species on the island. And so what we set out to do a couple of years ago is just to look at, okay, if we use our DAISIE model and we assume that we don't have phylogenetic data at all, the only thing that we know about the island is when it came about, so the island age, and the number of species that are on the island or in each clade that established on the island, and we know whether the species was endemic or not. If we can also do that with DAISIE, we can so basically say that we have missing phylogenetic data, and then we can estimate our parameters. And here's an example where we plot the colonization rate on the x-axis versus the net diversification rate on the y-axis, and we look at across many different simulations with the same parameter value, which is the parameter set, which is the black dot that we see here. This is the actual generating value for the simulations, and then for all those simulations we can then only take the diversity information, and then we can try to estimate parameters in again. So what we see here is that sometimes we do okay, we get estimates which are pretty close to the black dot, but in many cases we're just totally off. Now when we add information on colonization times, we already see that it gets better. Because a lot of the scatter on the lower bottom right side is actually is gone now, and it gets much closer to the black dot. It gets also a little bit better when you add branching times of the species, but that of course depends on how many clades were actually undergoing cladogenesis. So what we see is that phylogenies do add information, particularly for colonization times, but also branching times can be useful to get better estimates of the rates of these processes. Okay, I would like to return to the questions that I posed at the beginning. So first of all, are island communities in macroevolutionary equilibrium, and are the radiations that we observe, are they exceptional? Well, so we answered those questions for the terrestrial avifauna on the Galapagos Islands, where we considered an ecological guild of 25 species of passerines and allied species. We assumed an archipelago age of 4 million years. There is some uncertainty about that, so we also explored larger ages, where there's a maximum in the literature of 14 million years. And we treated all the islands as one. And that you might argue for two reasons that that's reasonable. First of all, that there have been Pleistocene connections between those islands. So because when the water levels were lower, it was actually a single landmass, or there were connected islands rather than separate islands. But also we're looking at birds, of course, that could fly between the islands more easily than many other species could. So we treat them all the islands as one, just as a single unit, and then applied our model to it. So the data looks like this. That at least the data that we used. So what we see here is in blue are all the endemic species and endemic clades, and in green we see the non-endemic species. So we see one species for which we actually know the colonization event, because we know from phylogenetic data when this island species actually diverged from its mainland population. And for the two species on the left, we actually don't know that. Well, we know that by now, but this was the data that we used in 2015. And in those cases, we can still take them into account, but we have to assume that the immigration event happened anywhere between the island age and the present. And we can still do that for many other cases where that information is missing. Okay, so what we did was we fitted many different models to the data, and I don't want you to go into all the details of this on the right, but just to show that there was many models that we considered, and they differed mostly in whether or not we considered the Darwin's finches to be different, so have different parameters, whether or not the Darwin finches are in equilibrium, and whether or not the non-Darwin finches are in equilibrium. So what we found is that the best model, the model that fitted the data best, was a complex model with differential diversification rates for Darwin's finches. So really, this model showed that Darwin finches do something special. They are actually exceptional. And so, what did we find, in fact, as our maximum likelihood estimates for this best model? Well, we found, first of all, for the non-Darwin finches, is that the limit to the number of species is actually undetectable. So it's infinity. It could be, of course, finite, and this is probably expected, but we couldn't detect it. So basically, the model says it's very large. It's infinite. We also found rates of colonization of 0.002, of extinction of 0.09, and of anagenesis of 0.87. And maybe those numbers don't tell you much, but maybe at least relatively to one another, it tells you a little bit of the rates of these processes. So there are events per lineage per million years. And the rate of cladogenesis was 0.2. And what you see here is that the rate of cladogenesis here is larger than the rate of extinction. So they will actually continue to grow according to this model. When you look at the Darwin's finches, where we kept the gamma and the lambda A, so the colonization rate and the anagenesis rate the same, but looked at different rates of speciation, sort of cladogenesis and colonization, we see that they actually do seem to have achieved an equilibrium, and also are subject to diversity dependence, because this K value was estimated to be 15. And what we also see is that they have a very large extinction rate and also a very large rate of cladogenesis. And so basically what this model suggests is that there is a lot of evolution going on in these finches, and maybe a lot of attempts are being made in these finches at evolving in different ways, and many of those attempts, they actually lead to nothing, they go extinct. But because there is actually continuously being replaced by new forms, which is the rate of cladogenesis. And I guess that's in line with what we know about these Darwin finches, that they do actually evolve exceptionally fast. And this is then also reflected in our macroevolutionary rates. Okay, so our second question was, are the Galapagos actually at equilibrium? Well, so when we look at the predicted diversity through time, we see that that it actually is increasing. So we have to note that there is a logarithmic type axis on the y-axis, and so we see that there is they are not at equilibrium except for the Darwin's finches. We also looked at some other cases, so the avifauna in Micronesia. So that's the Canary Islands, Cape Verde, Madeira, and the Azores. And so we also looked there, and what we found there is that they actually pretty much do reach equilibrium. So that might have to do with the size of the islands or other features. But what we saw in our estimates to these data sets is that they the predicted diversity through time reaches an equilibrium. Okay, now we'll move to question number 3. So what is the effect of human-induced extinction from a macroevolutionary perspective? Well, we answered this question by looking at bats on the Greater Antilles. So as you can see here where the Greater Antilles are located, and so Puerto Rico and Jamaica and Haiti and Dominican Republic, etc. And so we looked at bats, and we did the same kind of exercise in going from phylogeny to data, and then try to estimate the parameters. The difference here is that there was also information on some of the on the extinct species, and so we can also say something about what if so that we know that these species went extinct. So what does that actually have? What is what are the consequences of that? So what we looked at is that if you look at our we use our parameter estimates from the data, and we can simulate with that, and then we can look at so what are our predictions there, depending on what we find now. So what we see is the current diversity is in red, and the pre-human diversity is in black, and then the equilibrium diversity would be in blue. And so we see that these are different values. So of course, the pre-human diversity was higher than the diversity that we currently see, because humans drove those bats to extinction. And and what I would like to point to is that if you take away the species that went extinct from the pre-human diversity, and you would have to wait using the natural background rates of speciation and colonization, etc., until it reaches the same value of the pre-human diversity, you would have to wait at least 8 million years to reach that point. And maybe those islands by that time will not be in existence anymore. So that sort of sets a macroevolutionary perspective on how much damage we actually do in driving these species on islands to extinction. We lose species that we would never be able to get back again. Of course, we would never be able to get the same species back, but even the diversity levels are just cannot be reached anymore. So this is how much damage we actually take, even also from a macroevolutionary perspective. Okay, so we did similar analyses on bird species in New Zealand, where also after Polynesians arrived, there were 30 extinctions, and that was only 700 years ago. So these are some of those classic extinctions that people might know about, species that went extinct on New Zealand. But not only Polynesians, the first humans that arrived, drove species to extinction, but when Europeans arrived 200 to 300 years ago, they also drove an additional number of species to extinction. And there's currently also some threatened species. So we're just continuing to threaten those species on the island with extinction. And our question was, again, like, how does that affect our estimates, or how resilient these islands are, and how fast they could actually, or how slow maybe, how they get back to the pre-human levels of diversity. So here are some of the examples that are threatened or potentially under threat. So again, you have to get the phylogenetic data and turn that into DAISIE input data. And so here there was molecular data on 84% of species. Was also ancient DNA being used of 77 of extinct species, and some were just added as independent colonizations or to known clades, where we can take some of that into account in the method in terms of missing data. So what we found here is again similar results as in the case of the bats. Is that if we want to look at the return time to pre-human diversity, then the arrows actually give estimates to that. And so what we see is that those estimates, they're really large. So anywhere 5 to 50 million years you might have to take to actually go back to pre-human diversity. Also, if you look at if we actually drive the threatened species now to extinction, or if we drive the threatened or near threatened species to extinction, how long does it take to return to the same levels as before? And we see that these levels are really, really these times that it would take are really, really long. Okay. All right. So this was work done with these people that I mentioned here. So for a lot of the so Luis and I, of course, mostly focused on the Luis Valente and I mostly focused on the modeling aspects, but he was also involved in contacting many people on actually getting the data, because that's a massive undertaking to get the data, especially also for the extinct species. Okay, so I would like to continue, if I still have time, I think I do, to question 4. And that's the question is, how do the community assembly processes on islands depend on island characteristics? So what we know, and what I also introduced before, is that when we talked about the MacArthur Wilson model, is that as the area increases, the number of species increases, and MacArthur and Wilson attributed that to lower extinction rates. They also said that if the distance to an island increases, the number of species on the island decreases, and we see that also in our data. And this is nice data from New Guinea, birds of New Guinea, that was published in 1972. And we see also a clear relationship there. And MacArthur and Wilson attributed that to lower colonization rates if the island is far away from the mainland. So this is quite well known. So we know something about extinction and colonization as a function of island area and island isolation, respectively. But do we know anything about all these other relationships, about how colonization or cladogenesis or anagenesis depend on island area, or how extinction, cladogenesis, and anagenesis depend on island isolation? Is there anything that we can tell from the data? Can we use our DAISIE method to answer these questions? So we set out to answer this question by doing a global analysis of island birds. So these are 41 archipelagos around the world of birds, where we basically did the same thing as I showed before for the Galapagos. Is we try to get the data in that shape, and then combine all these archipelagos together in a single analysis. So, of course, that's not so easy to get that data. I mean, I was involved mostly at the point when the data was already there, but it involved quite a lot of work. Well, first of all, to get molecular data that's already available from GenBank, but also to obtain new DNA sequences by doing field work and museums and looking at museum specimens. And there was a massive amount of work again to get those new data. So what it resulted in is 91 dated source phylogenies, and the times of colonization and speciation of 581 taxa, and 110 of those were previously unsampled. So it was quite a large chunk was really new data that we added in this study. So what you could do, of course, is say, okay, let's just look at archipelagos. Let's get all the islands and get speciation rates from all these islands, and then you can maybe look at the speciation rate and then regress that against island area and get an idea of of this relationship, whether speciation rates of cladogenesis or anagenesis depend on island area. However, that doesn't seem to be the right approach to do because there might be some statistical issues there. So what we did is something else. What we said is that let's assume that there is a relationship between lambda and so the speciation rate, for example, and island area. And let's say that it's a linear relationship. And what we want to do is we want to find this M that maximizes the likelihood for the entire data set. So we have a slope that must apply to all these different islands across these islands. So this is what we try to estimate, is to do it not in two steps, where we first get the lambdas for each archipelago or for each island, and then do the regression, but do all in one go. So what we need for that is some assumptions on those relationships between the parameters, the rates, and features of the island, specifically area and distance from the mainland. So here's an example. So where we say the distance from the mainland or from the continent is a decreasing power law function the colonization rate is a decreasing power law function of the distance from the mainland, as we plotted here. And so we can do this for all the rates: colonization, extinctions, anagenesis, cladogenesis, and then we end up with parameters that are like these ones: the gamma zero, which is sort of the a rate at a particular distance, and then also the parameters like this parameter x that says something about the type of decline with distance. Okay, so I would like to do something if there's time to get you involved, because I would like to see whether this is possible, even though I cannot see you. I think if you have a device, I would like you to go to this website, www.kahoot.it, and let's see whether we can get that to work. I have to also switch my own screen because I have to go to the Kahoot. And okay, so I'm going to do a classic game of Kahoot. So go at kahoot.it, and it will tell you the game pin that you have to enter. So I'm seeing whether there will be anybody joining. Then I will also see whether there's anybody still left in the audience. So you have to enter this number. Hopefully that people can join. I see nobody joining.
I don't know if I'm trying. So what do I have to do?
Yeah, I see some people are joining now, but it might take a while.
Okay. Yeah.
Okay. You can still join, I guess, if you want to. So 206-5536 is the game pin that you have to enter. But I will start the Kahoot, and so I will do that. And you will have to answer some questions, and so you also have to be fast. So the first question: in what year did MacArthur and Wilson publish their book on island biogeography? And so these are the three answers that you can enter. And you have 14 seconds left to answer. I hope the internet is fast enough so you can enter, because I don't see any answers yet. Now people are answering. So you have to get it right. You also have to be fast to actually be the winner. So the right answer was 1967. And maybe some of you guessed, some of you knew. The other dates were also important. 1963 was, in fact, the the year that MacArthur and Wilson published their first article on which their book is based. And 1971 was the year that I was born. So it's also, I guess, at least for me, a significant year. Okay, so we'll look at the score list, and Joachim is in the lead now, but there's a few more questions remaining. And those are for about what I just said is, what is your guess in how colonization rates depends on area? Does it increase, does it decrease, or does it not depend on area? Okay, so the right answer is colonization rate does not depend on island area. At least that's what the data tell us. Maybe you might think that it does depend on island area, but the data told us, no, it doesn't. At least the best model didn't depend on that. Okay, let's look at the score list. So Lucas has now come in first place, but let's see, there's still a few more questions left. So how does the rate of cladogenesis depend on area? I see 0 answers. There the first answers come in. 4 seconds left. Be quick. Okay. The right answer is indeed red. Cladogenesis rate increases with island area, according to our results. And now Christoph is the one that's in the lead. Okay, let's go to the next question. How does the rate of anagenesis depend on island area, according to our data? Okay, 3 answers were correct. Anagenesis rate does not depend on the island area. All right, let's go on and see that Dave is now in the lead. So the number 1 is changing all the time. Okay, number 5. How does extinction rate depend on isolation? So the more isolated, the further away from the mainland. Okay, so what we found is that there is in fact extinction rate. There is in fact no relationship between extinction rate and isolation. Okay, let's look at the scoreboard. Okay, so David in the lead. Okay, let's go to the 6th question. How does the rate of cladogenesis depend on isolation? Okay, the right answer is cladogenesis rate increases with isolation. Very good. Okay, let's look at the scoreboard. And Dave is now strongly in the lead. And for the last question, how does anagenesis rate depend on isolation? Does it increase with isolation, decrease, or does it not depend on isolation? Okay, so anagenesis rate increases with isolation is the right answer, according to our data at least. Okay, so we look at the podium. So Joachim got 3 out of the 7 questions correct, and so Christoph also got 3 out of them, and 4 out of the 7 questions were correctly answered by Dave. So he's the winner of this little Kahoot. So there were some runners-up, Lucas and Ramiro, I see. So I will go on. So why did I show this little Kahoot? Well, so apparently it's not that trivial, because not all answers were correct. So this is what we found in our data, and I will just summarize that again. Again, is that we found that colonization declines with isolation. anagenesis increases with isolation, extinction declines with area, and the rate of cladogenesis increases interactively with area and isolation. And by that I mean that depending on, so the relationship with area is different for islands that are near the mainland and then for islands that are far away from the mainland. So there is a cladogenesis increases with both, but in this interactive way. And so the formulas that are listed here are the ways, actually the formulas for the best model. So these parallel relationships for cladogenesis, extinction, anagenesis, and colonization. Okay, so you may wonder, well, that might be all okay, but does it really, is this model really a good fit of the data? So here's just showing the model fit for the total and the total number of species, the cladogenetic number of cladogenetic species, and the colonizations. And so the three dots here show those fits. And so we have black are well estimated, red is underestimated, and blue is overestimated. And we see that most of them are black. There is a little bit of underestimation and overestimation here and there. And particularly 38, there's islands there that in the Gulf of Guinea that are underestimated. So in fact, you could say that this is really the hotspot of island biodiversity, is that our model that is based on all these archipelagos across all the world, it predicts a lower diversity than we actually observe on these islands. So there is something really going on there, and they're sort of almost forgotten islands with high biodiversity. But it might be interesting to see that from this analysis we get a different answer on biodiversity than you might have expected to happen. For example, Hawaii is not that far off from normal. There's a little bit of overestimation, in fact, in number 37. But it's the islands in the Gulf of Guinea that are actually a hotspot. Okay, so I don't think there's a lot of time left. So I guess I'll skip through these ones. These were just to show that it's not just a random result we can get. So red arrows show what we observe. And if you just randomize, then you would get the gray result. So it's really far off. So it's not just some fit. We really have found something interesting. And again, I will just skip through these ones, except to show that also our pseudo R squared for our model fit was quite high, around 0.7, 0.8 on the different predictions. Well, so the conclusions from this is that this is the first empirical evidence on a global scale to show a relationship between anagenesis and isolation, which you might have guessed, and so many of you actually got this right, is that the further away the island is from the mainland, the more likely it is to undergo anagenesis. But this was actually the first study to show that relationship, and also a relationship between cladogenesis and area and isolation. So, and that the effect of area is mediated by isolation. Maybe from just thinking about it, it might sound reasonable, but our data shows this for the first time, we believe. It also confirms relationship that we sort of already knew between extinction and colonization and area and isolation, as MacArthur and Wilson also already assumed or observed. So for this work, these people were all involved. Luis Valente led most of the work in terms of all the analysis that were done. I was mostly involved in developing the methodology, and many of the other people were involved in actually getting the data to do this global study. I have another question that I would like to address, but I think my time is up. So I give the floor back to Renan, and maybe have still time, a few minutes for questions.
You come on the show if you want to present or not. It's up to you.
Well, sorry.
It's up to you. If you want to finish the presentation, that's okay. You have a little.
Okay. Well, maybe go on. If people need to leave, then they leave, I guess. And then if this thing is recorded, they can watch it later, I guess.
Yeah.
Okay. Well, then I'll continue on question 5. So question 5 was, how do processes of community assembly on islands actually depend on the species that are already on the island? So remember that I already introduced this clade-specific and island-wide models. And this is sort of based on Darwin's quote in his famous book on the origin of species, which has been later called the competition relatedness hypothesis. And he said, as species of the same genus have usually, though by no means invariably, some similarity in habits and constitution, and always in structure, the struggle will generally be more severe between species of the same genus when they come into a competition with each other than between species of distinct genera. So you may wonder that, this idea of clade-specific diversity dependence means that only species within the same clade that are very similar, they will affect each other. So Darwin was thinking in terms of evolutionary effects. Here we are extending this to macroevolutionary effects, is that they affect the speciation and colonization of other species. So the clade-specific one says it's really restricted to very similar species, whereas the island-wide model says it applies to all the species on the island equally. So which is not really in line with this hypothesis of Darwin's. Just to say a little bit more about what do I mean by this diversity dependence? Well, diversity dependence means that the speciation rate or the colonization rate depends on diversity. So as diversity increases, the speciation rate or the colonization rate, it will go down. So the simplest model that we can take for this is just a linear decline, right? As diversity increases, the speciation rate will go down. And what we will see is that there is a diversity at which the extinction rate and the speciation rate are equal to one another. And we call that the carrying capacity. There is also a diversity at which the speciation rate becomes zero, right? So here at 10, diversity of 10 species. So this is sort of the limit. This is what we call the K prime before. So the K with the prime next to it is really the upper limit of the number of species, because beyond that, there would be no more species being formed because the speciation or the colonization rate would be zero. So, so the question then is, we know that you can have this diversity dependence, and maybe I'll just ignore this part about the key innovations. But the question is, what is the zone of influence of diversity dependence? Does it extend to very similar species only, or does it apply to also very distant clades? And particularly on islands, does it apply only on very similar species that descended from the same colonist, or does it apply to all the species on the island? So we looked into this and we applied this to Caribbean rain frogs. And so this is a nice case where there is five colonizations that happened, or at least five. Only 5 of them survived because we have data on them. And they also have radiated. And it's also interesting to see that all of these have diversified also in different kind of niches. And so we thought, okay, well, if the island-wide diversity-dependent model would be applying, it might be applied in this case particularly because these frogs, they in each clade they occupy similar habitats, so they would be affected by one another, right, across different clades. Well, let's see whether that was the case. So here are the 5 clades that we identified. So we know that this idea of different ecotypes within each clade that is repeated across clades, and we think that might be actually a signal of island-wide diversity dependence. But does the phylogenetic data actually tell us the same story? So what we found by applying this island-wide model with all that mathematics that I showed you before, that we found that the clade-specific model was actually clearly preferred. So contrary to our initial ideas about that this might be a clear case of island-wide diversity dependence. So what we found, for example, is that the AIC weight of the clade-specific model was 0.998. It's really, really high. But there is a warning here, because we know from previous experience that the likelihood ratio test, or using AIC for models that involve diversity dependence, they might actually yield biased results, where you might say that your type 1 error, for example, is only 1%, but it is much higher than that in reality. So we wanted to check this by doing a bootstrap. So what do we do in a bootstrap? Well, we can simulate data sets that follow the assumptions of the clade-specific model. And we can do that same thing for data sets that follow the assumptions of the island-wide model. So we can simulate according to those two rules. And we use the parameters that we obtained by fitting the two models to the empirical data for the frogs. And then for each of the simulation data sets, we can fit both models to that. So we get 4,000 estimates, right? So if we have we have 1,000 CS data sets, and we fit the two models to it. So we get 1,000 for each model. So that's 2,000 for that for the CS data sets. And we do the same thing for the island-wide data sets. And what we found is that if we used AIC, that in 7.7% of the CS sims, we would the AIC would actually incorrectly lead to the island-wide model as the best model. And maybe you can say, well, this is sort of acceptable. But what we also found is that when you look at the island-wide simulations, then 90% of those simulations would actually be identified by AIC as a CS model. So that the CS model would actually be the best fit to it. So we would really make a big mistake. That's in almost 20%, a fifth of all cases, where there is actually island-wide diversity dependence. We would say, well, it's actually clade specific, and that would be wrong. So the question is that we find this very high AIC of weight of 0.998 in this case, but how reliable is that selection of this clade-specific model here? So we developed a new method based on a bootstrap likelihood ratio test to really make this clear. And so what we found is that if you look at the likelihood ratio or the log likelihood difference between the two models, again, you take all those simulations and you can look at the and use the two models to fit to those simulated data sets, and then look at the distributions of the likelihood ratio. And so the black arrow here it points at the empirical value of the likelihood ratio, what we find for the rain frogs. And the other arrows actually tell us something about how likely it is to find this result, or not this result, but to find 5% actually deviation or mismatch in what we identify as the right model. So in the case of CS simulations, the fifth percentile would be the case where we actually identify the IW model as the right one, and the 95th percentile would be for the IW simulations would be the sort of what we allow to make an error in identifying it actually at CS cases. So what we find is that both of these arrows are much lower than the black arrow for the real data. And particularly if we identify this now as a CS model, it's very unlikely to be a wrong identification. So the p-value is smaller than 0.001. So there was actually not a single simulation out of those 1,000 simulations where we found that the log likelihood ratio was larger than what we found in the empirical data. So the empirical data really, really, really strongly point to the clade-specific model. And that is, again, odd because we sort of started out by thinking that this might be a case of island-wide diversity dependence. You might think, well, maybe the models just don't do a good job at all. I mean, you might compare two models, but if they both perform poorly, then what does it tell you? So you can look at the goodness of fit of the models, and this is what we did. We simulate again with the model, and then we can compare with the empirical values. So the empirical values for the number of species, the number of colonization events, and the size of the largest clade, and the rank of the largest clade. So which one was, the largest clade, was that like the first one to colonize or the second one to colonize? Those, if we look at those statistics and we look at the distribution across the 1,000 simulations, or in fact, in this case was even about in 5,000 simulations, then the blue arrows, which are the empirical data, they are very close to what we find in the simulations, in the median of the simulations, right? So the black line is the median of the simulations. So this is also slightly better on the CS model than on the IW model. So the IW model also does a reasonable job, but you can see that, for example, if the size of the largest clade is a little bit off although it could still be very much possible under the IW model, right? So it's not like it's in the tail of the distribution, but you can see that the CS model seems to do a much better job than the IW model in this respect. So that is reassuring that at least the models do a pretty good job in fitting to this data. We could also look at the parameter estimates themselves. We can look at whether the parameters that we estimate from those simulations are pretty close to the parameters that we generated them with. And we again find that this is really close. So there's little bias in the parameters that we find. There's a little bit more bias in the case of the IW model. And again, this might suggest that the CS model is indeed really doing a good job. So to conclude with this, and then also, I guess, to conclude with the entire talk, is that what we've established here is a new method to distinguish clade-specific and island-wide diversity dependence. It's made available in our package that we made, the DAISIE package. And particularly for these rain frogs, we found evidence for clade-specific and not island-wide diversity dependence. And so the fact that we find repeated patterns of diversifying into the same ecotypes might indicate that evolution is not completely parallel, but there are actually niche differences between the different clades. I must add one caveat is that some of the clades are actually alloclades. And what I mean by that is that if we look at the different clades, the 5 clades, is that they appear on different sides of the islands, in this case, island of Hispaniola. So that might have something to do with it, is that those clades don't even meet each other. But the question is, of course, is that a result of diversity dependence, or is that causing the absence of diversity dependence, that they actually don't interfere? But it could also be that we don't find them together because there is actually diversity dependence. So looking at alloclades doesn't really resolve that question either. So by just ending with acknowledging the co-authors on this work as well, I would like to end my talk. And if there's any questions, I will go on and answer them. Thank you for your attention.
Okay, thank you, Rampal. Thank you very much. It was an amazing talk, amazing game. I'll move it right away for the questions of everyone. I think you can see it now. I will read it anyway. So first questions from CFG Nets. Great talk. Thanks, Rampal. If arrival dates of non-endemic immigrant species are considered unknown, does this lead to a consistent underestimation of immigration rate?
So the way we, as I explained, we take this sort of missing data into account by just saying, well, it's anywhere between the island age and the presence, right? So the model actually is going to find sort of the best fit, and maybe what we could do, we haven't actually done that, is to say something about, when is the most likely date of arrival. We haven't actually found really any effect of underestimation of the immigration rate because of this uncertainty, right? So it doesn't also necessarily lead to that, because we're not actually biasing our results in any way. We just, it would be the case, I guess, if our model wasn't actually fitting the data very well. But we haven't looked into this in particular.
Okay. A question from Jefferson Bugoni. In some case, as for Darwin finches, hybridization is known to play a role both by producing new species or collapsing existing species. Does it make sense to incorporate hybridization into the model?
Well, that's a good question. We would, of course, try to avoid hybridization, but again, this might be true for finches. The thing is, of course, that the question, of course, and when you have hybrid species, whether the phylogenetic tree is actually even a good way of reflecting the evolutionary, macroevolutionary history. So I think we have to think about that if hybridization is something to incorporate. But I think we would first have to do this for single clades and do this well until we actually move to DAISIE. If we can do it for single clades, we can also do it in our island work, I think. But it's an interesting suggestion.
Mm-hmm. A question from Ana Carnaval. Thank you, Rampal. I would love to hear your thoughts about using DAISIE to explore drivers of interspecific diversification on island-like systems, and she continues. While assumptions that apply to extinction parameters of full species may not apply, maybe it can allow us to explore how ecological traits, islands features impact phylogeographic structure.
Yeah, so I think it's a good question because we defined the rates of anagenesis and cladogenesis, of course, on the species level. But these are just rates of formation of species. So if you want to say, well, I want the rates of formation of subspecies, that's the model doesn't care about that. I think the phylogenetic information for that is a little bit more difficult because if you look at lower than the species level, then maybe it's much harder to get good trees for that. But in principle, it's possible. A model doesn't care. I mean, then you define your units as subspecies, for example, and you can then answer the same questions.
Mm-hmm. Mm-hmm. Have you done that?
Not really. No. Usually we play it at the thing is that it's already difficult to find this type of data for species level phylogenies, right? So where it's at least seems to be clear what the phylogeny looks like, but yeah, I mean, if there's people around that want to play with it, then feel free. I would also love to talk about it. Yeah.
Okay. Another question. In Rio Grande do Sul, we have a lake system that could be a good region to test those hypotheses and non-oceanic island. To be honest, I'm not well familiarized with this subject to do this affirmation, so our formulators make a question. What could be a good non-oceanic island region to test the DAISIE framework?
Well, it's a good question. The question is, first, I guess, what a non-oceanic island, what that is. So we've also done some work, especially particularly in simulation work on non-oceanic islands where islands actually don't have an origin, where there's like a volcanic eruption and then the island comes about, but where the island is actually formed by breaking off from the mainland. I mean, if that's the definition of a non-oceanic island, then DAISIE actually turns out not to be a good fit because then actually there are initially already islands, species on the island when it breaks off from the mainland, right? So that makes it really different from an oceanic island. But if you mean by oceanic island just something that is not a marine island, like the Sky Islands and lake systems that I showed before, but where you could still say that, okay, it just came into existence at some point, then yeah, I mean, like the marine lakes that I showed or the Sky Islands could work. And maybe that lake might also be a good case. We have actually applied it once. It's actually was a postdoc that contacted us who wanted to work on a lake in Germany. Not in Germany. He is from Germany, but in Japan. And yeah, so it can be done in that case as well. But we have to look at the specifics of the system, whether we don't violate the assumptions too much. We do know that some of the violations of the model assumptions are okay. It doesn't matter. Model is always violating reality, right? But yeah, we have to know more specifics of the system to know this. So if you want to talk about it, feel free to contact me afterwards.
Thank you, Joaquin, for the question. There's one more question here from Luisa. Thanks for the great talk, Rampal. Is adaptive radiation on islands the exception?
So we tested, of course, only for radiations. Whether they're adaptive or not, that's not really in our model, right? So that's a different discussion. So what we showed is that at least for the Darwin finches, we said that, okay, it's exceptional because the rates at which they diversify, the Darwin finches, is different from the other birds on the island. So in that sense, yes, they are. But whether it's true for all the other radiations, well, we would still have to test that.
Okay, a lot of cheering for your talk.
Yeah, I see it. Thank you.
Yeah, thank you very much. I have a few questions. Well, first, if you have shown us that isolation impacts on speciation, there is more speciation, relatively more speciation on more isolated islands, and I wonder why is that? Is that because of the reduced gene flow and the frequency of recolonization in like impacts these rates of speciation?
Yes, yeah, that's indeed the case. I mean, so at least that's the expectation, is that as gene flow stops, it's of course more likely to undergo alegenesis, to really diverge from the mainland. But also the cladogenesis apparently also increases as as the island is further away from the mainland. Again, I think because of gene flow stopping otherwise the speciation process.
Mhm. So in this case, if you have a clade with say very low dispersion rates, then it could have high speciation rates even in close islands.
Yes, that could be a case, right? So if we find that, I mean, here of course we studied birds. So for birds, you also have to make the distance a little bit larger because they can of course easily fly short distances. In other taxa, you could imagine that you could have even short distance from the mainland, but then of course it always becomes tricky in terms of, are those species then that you find there, are they actually native or are they introduced by humans? Usually if they're small, right, they might, and especially also plants might be in many introduced species. So that's then the other challenge, is to separate those.
Mhm. Okay, thank you. Uh, if there is not any other questions, then I will finish here.
Okay, thank
Okay.
you.
Okay.
Obrigado.
So thank you, Rampal. Thank you, everyone, for being here today. And see you.
All right, bye bye.